Hey guys, and welcome back, and today we're going to be talking about dilations. Our learning target for today is going to be to explain the effect of dilations on two-dimensional figures. We're going to be successful doing this by identifying a dilation as a reduction or an enlargement. Those are going to be two vocabulary words that we're going to go over. And then we're going to find the coordinates of the image given the pre-image coordinates and the scale factor. So, the key idea here of a dilation is we're going to be changing the size of a specific figure. Our definition says a dilation is a transformation, so just like translation, rotation, reflection, this is a fourth transformation that moves each point along a ray through the point starting from a fixed center and multiplies the distance from the center by a common scale factor. If the vertex of a figure is the center of dilation, then the vertex and its image after the dilation are the same point. So in this picture, none of the vertices of triangle ABC are the center of dilation. The center of dilation in this example is 0, 0. So when you dilate and you give a center of dilation, it's almost going to telescope in or out. If you make the shape bigger, it's going to the center of dilation is going to push the figure away from it. If you're making something smaller, it's going to pull the figure in towards it along these paths. Now with a straight edge, what I would do is I would make... Now I don't have a straight edge, but if I were you, I'd use a ruler and I would draw lines from the origin, which is our center of dilation. You know what? I'm going to make this a little more straight. There we go. You would draw the lines from the center of dilation through each of the vertices. And then you would use your scale factor to slide the points along this path. So if you notice, if I wanted to make this shape 2 times bigger, I would have to, from the center of dilation, rise 2 and run 1 to get to point A. So if I want to double that distance, we're going to rise 2 and run 1 again. So that's where A prime would be. Same thing with B. I have to rise 4 and run 3. We'll do that one more time. Rise 4 and run 3. As you can see, it landed right on that red line that we connected from the center of dilation through the origin. Same thing with A prime. A prime still landed on one of the red lines. B prime landed on one of the red lines as well. And then my last one, C, we rise 1 and run 4. You can rise 1 and run 4 more. Again, you can see that lands on this red line that we created through the center and through the vertex. That's going to be C prime. And when you connect all these new points, you get a triangle that is double the size of your original, just by making it double the distance away from the center of dilation. It almost looks like a telescope kind of image. Okay, and an example of when you actually have a vertex on the center of dilation, so this is a rectangle and the center of dilation is 0, 0, that would mean that D, or I should say D prime, does not go anywhere because it's sitting on top of the center of dilation. So it actually stays right there. But if we wanted to enlarge this image to be 2 times as big, again, you want to draw straight lines from the center of dilation through all of the vertices, straight as you possibly can. And then you're going to shift the points down those lines. It's like B is going to be moving in this direction, C is going to be moving in that direction, A is going to be moving in that direction along the red lines to be double the distance. Well, C is 3 units away. You can count that. Okay, 1, 2, 3 units away from the center. So if you count another 3, 1, 2, 3, you've just doubled the distance it is away from that center. So you can do the same thing with B. C, we were able to count just horizontally. B, we would have to do a rise and a run. For B, we have to rise 2 and run 3. So if you rise another 2 and run another 3, we get B prime right there. We had C prime down below, B prime right there. And then A is only 2 units away from the center, so if we count 1, 2, and then 1, 2, we've just doubled the distance. So there's A prime, and then it creates this rectangle right here. Okay, in both those examples, I talked about enlargements. We are also going to study reductions, or making the shapes smaller. So let's take a look at our first example. Only thing I want you to do here is just identify which one of these is actually showing you a dilation. All right, so I'm going to just note the things that I'm seeing in each of these graphs. Like in the first one, I'm not seeing a size change. So no size change. That should tell me that it's not a dilation. In fact, what I'm seeing here is a translation. Okay, so this one is not a dilation. The second one looks like I have 2 different size triangles, so I just want to confirm by double checking and seeing if their proportional side, or their side lengths are proportional by setting up a ratio like we talked about yesterday. So from B to C, I see that that is 3 units long, and from B to A, I can see that that's 2 units long. I'm going to compare that now to B prime to C prime, which I see is 1, 2, 3, 4, 5, 6 units long, and B prime to A prime, which is 4 units long. So as we discussed yesterday, 2 figures are only similar if their ratios of their side lengths are equal. So I see from the black triangle, 2 and 3. I want to know if that is proportional to, or is equal to, 4 over 6. Okay, and I know that 2 and 4 should be the numerators. 1, I just chose for 2 to be a numerator, but if I choose 2 to be a numerator, 2 corresponds to 4 because they both represent A and B, going from A to B, and A prime to B prime. So now I'm just going to, you can type this in your calculator, or you can just try to reduce the fraction. I'm just going to type in my calculator. When I type 2 divided by 3, I get 0.6 repeating. And then when I type 4 over 6, I get 0.6 repeating. So this is a true equation. So I would say that the middle picture definitely is a dilation. Now, the third one looks like the shapes have been warped. So I'm just going to double check using my proportions to see if their ratios are equal. From B to C, I see 3 again, and from B to A, I see 2 once more. And then on the other triangle, I'm seeing from B prime to C prime is 4, and from B prime to A prime is 1. So if I take the side lengths from the original triangle, ABC, I get, again, 2/3. I want to know if that's equal to, since 2 is the shorter side, 2 should mark up with 1, which is the shorter side on the image triangle. So 1 would correspond with, or I should say 4 would correspond with 3. So now I'm just checking 2/3, is that equal to 1/4? Well, 2/3, as we know, is 0.6 repeating, and then 1/4 is actually 0.25. So these two are not equal. Seems like maybe the triangle was stretched out horizontally and then squished down vertically. That is not a dilation. A dilation stretches or shrinks all dimensions of a figure in the same way. So the middle picture here was a dilation. So why don't you guys give this a try? I want you to identify which one of these pictures shows a dilation. All right, so before we get to example 2, I wanted to give you a little intro on our vocabulary words, which one of them is enlargement. I want you to think of the word enlargement as having the word large in it, so it's going to mean to make larger. It's a dilation with a scale factor greater than 1. Think about a scale factor. Okay, I'm going to write this down. Scale factor multiplies one figure to get the other. Okay, key word here is multiplies. Okay, all scale factors are going to multiply side lengths to get other ones. So if we think about this, multiplying numbers by anything larger than 1 is going to make the number bigger. If we multiply by something smaller than 1, it's going to make it smaller. So you can see here the scale factor is 3, and you can tell from 0 to C, that's 3 units long, but from 0 all the way to C prime, that's 9 units long. Okay, so 3 times 3 is going to equal 9. So I see my scale factor in what I need to multiply the side length by to get the new side length. And it would work on all sides. Just like from D to A, okay, so from here to here, that's 2 units. But from here all the way up to A prime, that's going to be 6 units. 2 times 3 is equal to 6. So that 3, again, is showing the scale factor. It's always going to be what multiplies the side length of the original figure to get to the new one. And this is my example of my reduction. Now, reduction, we just have to think of the root word, which is reduce. Okay, to make something smaller. And again, my scale factor is going to be less than 1. I am going to add a stipulation to that. It has to be positive. Okay, once you start multiplying by negative numbers here, that's actually what's going to cause shapes to start flipping and turning. So when we dilate something, it's going to be a positive number. Less than 1 is going to reduce, like the number 1/3, which if you notice in this picture, it kind of looks like the last graph we had, only this time the image is the smaller rectangle, and on the last slide, the image was the larger rectangle. So it's the same dimensions, only we're showing the dilation from the larger rectangle to the smaller rectangle this time. And if you notice also from enlargement to reduction, a scale factor of 3 kind of resembles that of a scale factor of 1/3. Okay, only a scale factor of 3 makes it 3 times as large. A scale factor of 1/3 makes it 1/3 of the size. So now we're going to put this into practice in the second example. It says, for the given dilation, find the scale factor, then decide whether the dilation is an enlargement or a reduction. Okay, so I'm just going to take note of some side lengths here. If I were to look at from P to Q, that's going to be 4 units. And then from P to S, that's going to be 3 units. On the image figure, from P prime to Q prime, I'm seeing that that is 8 units. And from P prime to S prime, that's going to be, looks like 6 units. I'm going from 2 to 8, yep, 6 units. Okay, so now I'm just, and really someone yesterday had said this, you might even be able to notice what number you could multiply one side length by to get to its corresponding side length. So what can we multiply 4 by to get to 8? Seems like 2 is the answer. We'll double check that with the other side. What can you multiply 3 by to get to 6? Again, that would be times 2. So our scale factor here is 2. Now, being able to think about it in your head like that only works if your scale factor is a whole number. So if you're ever uncertain of how to calculate the scale factor, it's always going to be the image length, write this down, image length over the pre-image. Okay, that's important. Okay, so I can show you this. If I were to take 8, which is the image side length, and divide it by the pre-image side length, which is 4, 8 divided by 4 is 2. Same thing with the image length of 6 divided by the pre-image length of 3 equals 2. So my scale factor here is 2. So let's have you, forgot one thing. We needed to decide whether this is an enlargement or reduction. Now, because the scale factor is larger than 1, I'm going to write that down, larger than 1, this is an enlargement. Okay, so I'd like you guys to give this a try on your second U-try. For the given dilation, find the scale factor, then decide whether the dilation is an enlargement or a reduction. Alright, so I have another little intro here for example 3. This is a way we can find out the coordinates of our dilation without actually having to slide the points down that straight line that was connected through the origin. So it says to find the image of a figure in the coordinate plane after a dilation with center 0, 0, you can multiply the x and y coordinates by the scale factor. To find the coordinates of the image of triangle ABC after the dilation with center 0, 0 and the scale factor of 2/3, multiply the coordinates of each vertex by 2/3. So I have the first vertex written down here as an example. So if you notice, the point A right there, that is at, I can see that's 3, 6. Okay, so they wrote 3, 6. Okay, if I want to know what A prime is going to be when it is 2/3 of the size, you're just multiplying the x value by 2/3 and you're multiplying the y value by 2/3 to get the new point. So in your calculator, I don't want you rounding what 2/3 is, so what you need to punch is 3 times 2 divided by 3. That little 2 divided by 3 piece in your calculator really is just 2/3. Okay, you can also use the fraction button. Some fraction buttons on calculators look like this, where it'll say A, B over C, or some of them might say N over D for a numerator over denominator. You can use any of those buttons as well to represent the division symbol in your fraction. So 3 times 2 divided by 3 is where the 2 comes from. And then also to do that to the 6, okay, it would be 6 times 2 divided by 3, which is where the 4 comes from. So that means A prime, I'm going to plot, is at 2, 4 right there. Okay, and now I want to just continue getting the new coordinates by multiplying each one by 2/3. So B is at, looks like 6, -3. So if I multiply each of those numbers by 2/3, 6 times 2/3 is 4. And -3 times 2/3 is -2. So now I'm going to plot 4, -2 for B prime. Lastly, I got to find C. So C is originally at -3, 3. Multiply both of those by 2/3. We get C prime is going to equal -2, +2. -2, +2 is right there. So that's where C prime is going to be. Connect the dots. And we'll have just created a triangle that is 2/3 the size of the original. Okay, and notice how the triangle doesn't just end up shrinking into the center of the original triangle. It's shrinking, but it's also being sucked in towards the center of dilation at 0, 0. Okay, if I were to draw lines from the center through each of the vertices, they would line up in a straight line. Okay, that's what dilations do. They telescope in and out from straight lines from the center of dilation. So let's try this in the third example. We're going to plot the vertices for A, B, C, and then we're going to use arrow notation to find the coordinates of A prime, B prime, C prime after a dilation with a scale factor of 3. Okay, so first let's get our X and Y axes down. And get A, B, and C plotted. A is at 1, 2. B is at -2, 1. And C is at -1, -1. There's our triangle. And then I'm going to use arrow notation. So A, which is at 1, 2, goes to A prime. B, which is -2, 1, goes to B prime. And C, which is -1, -1, goes to C prime. And we just need to now figure out what all those coordinates are and plot them down. Well, it says all we have to do is multiply all of the X and Y coordinates by a scale factor of 3. So 1 times 3 is 3. 2 times 3 is 6. -2 times 3 is -6. And again, 1 times 3 is 3. -1 times 3 is -3. And again, -1 times 3 is -3. So now I can plot my image points. 3, 6, that's up here. So there's A prime. B is -6, +3, so right there. And then C prime, -3, -3, down there. And there you have a triangle that is 3 times as big as your original triangle. And again, notice how it's not just blown up around the blue triangle. It actually lines up from the center of dilation, and then the vertices form a straight line. Okay, just like that. Okay, you don't need to draw in those green lines that I drew in. I just want you guys to see that they do line up with the center of dilation. So let's have you guys give this a try. Alright, so I've got one more example for you, and this is actually to prime you for an activity that we're going to do with indirect measurement. It says your friend wants to find the height of a building. The building casts a shadow 15 feet long. Your friend casts a shadow 3 feet long. If your friend is 5 feet tall, what is the height of the building? Now, the idea here is that where the sun is, when the sun casts a shadow, it's going to cast a shadow at the same angle off of your head than it does a building. And what this does is it creates similar triangles. So the triangle that is created between you and your shadow, and then a triangle that is created between the building and its shadow. Okay, so similar triangles. One is big, one is small. Okay, so what we want to do is first look at which sides correspond to each other and set up a proportional ratio. So let's say we don't know the height of the building, so let's call that X. Okay, we want to be organized, just like we were doing when we were figuring out unknown lengths of any similar figure. So let's do, our categories will be something like, let's do like me and the building. And we also need to organize that. So let's have the numerator be the height and the denominator be the shadow length. So the height, or I guess it shouldn't be me, I guess it should be your friend. The friend. Okay. The height of your friend is 5 feet. And the shadow of your friend is 3 feet. Whereas the building, we don't know the height, but we do know the shadow, which is 15 feet long. Okay, so now if you remember, all we're doing is cross-multiplying and then solving for x. So when we cross-multiply, we do 3 times x, which is just 3x. And then we do 5 times 15, which if you grab your calculator, is going to be 75. Then we divide by 3 on both sides so that we can get x all by itself. And we get x is equal to 25. So the building here is 25 feet tall. Okay? So there are actually lots of real-life situations where you may see similar triangles, and you can indirectly measure the height of something that maybe you can't reach the top of to be able to reach it like with a tape measure. So let's have you give this a try in your 4th U try. It says, a 4-foot vertical post casts a 3-foot shadow at the same time a nearby tree casts a 24-foot shadow. How tall is the tree? What always helps me on these problems is actually drawing out a diagram. So we have a post that is 4 feet, and it's casting a shadow that is 3 feet. And then a nearby tree a tree that's casting a shadow. Okay, and this tree, let's see, it's casting a 24-foot shadow, and we don't know the height of this tree. So it's created similar triangles because of the shadows. The sun is creating the same angle off the top of these things. So again, let's split this up into, I'm just going to help you organize it before you solve it. I want you to set it up where you have the pole equaling the tree, or the post, I should say. And in that ratio, I want you to do the height over the shadow again. So go ahead and set that ratio up and solve for x. Alright, now just to wrap up this lesson, please write your open responses in the Edpuzzle boxes for these 2 close and check questions. Please make sure you get help if you have any trouble phrasing your thoughts. I will be looking over your responses, and it is going to tell me how much you actually understood about this lesson. Alright, that just about wraps it up. We explained the effects of dilations on 2-dimensional figures. And just so that we can recap here, we defined reduction and enlargement in example 2. We really just identified dilations in example 1. And then for the second success criteria, it says we can find coordinates of the image given the pre-image coordinates. We did that in example 3. Okay, we did also do an extra example, example 4, where we did some indirect measurement, and again, we will be revisiting that process once again. Go ahead and make sure you ask any questions. Feel free to rewind, go back, and make sure you understand every part of this video, and you may go ahead and start your homework.